A single hairline fracture at 6,000 feet can trigger a continental energy crisis. We're analyzing the extreme physics of the deep sea, where metal meets its breaking point, uncovering the hidden tension defining our borders and the future of global industry. Our entire global logistics network relies on infrastructure we can't even see. When we descend from the sunlit surface down into the absolute pitch black of the bathypelagic zone, the rules of physics shift entirely. This diagram illustrates Pascal's principle in action. In fluid mechanics, external hydrostatic pressure increases in a direct linear ratio to water depth. For every meter we drop, the raw weight of the water column pushing down on a submerged pipeline grows heavier. At the 3,000-meter mark, those physical loads threaten a complete collapse depth scenario. Standard industrial materials reach their physical breaking point as the extreme external force attempts to crush the pipe inward. The sheer weight of the ocean acts as a kinetic hammer. It ruthlessly exploits microscopic manufacturing imperfections in the steel, tiny geometric deviations from a perfect circle, known as initial ovalities. Even a fraction of a millimeter of distortion gives the water pressure enough leverage to cave the metal in on itself. This intense physical pressure acts as an invisible, unyielding ceiling. It strictly dictates exactly where and how global energy can safely travel. To survive these crushing forces, engineers employ a highly specific material science countermeasure, high-yield carbon steel, specifically an industry grade known as API 5L-X65. But strong steel is only part of the equation. Architects rely on ultra-thick walled pipes, aggressively skewing the diameter-to-thickness ratio. By shrinking the internal diameter and heavily reinforcing the outer wall, they counteract the massive hydrostatic loads. The global transition to green energy introduces a severe mechanical complication. Producers are attempting to pump pure hydrogen through subsea networks originally designed for heavy natural gas. This animated microscopic view illustrates hydrogen embrittlement. Tiny molecules permeate the solid steel, slipping between iron atoms and forcing the crystalline structure apart. The result is a fatal compounding risk: external deep-sea pressure crushing the pipe, simultaneously with an internal element weakening the metal. Energy producers are caught in a permanent balancing act between the staggering financial cost of over-engineering their materials and the catastrophic risk of a pressure-induced implosion. The physical vulnerability of these deep-sea pipelines make them the most exposed infrastructural choke points on the planet. As this aerial photo shows, the destruction of the Nord Stream system serves as the ultimate baseline case study for infrastructural sabotage and geopolitical fragility. The destruction of these lines highlighted a critical vulnerability. The largest energy reserves on the planet are functionally locked away if the physical arteries required to move them are severed. In this environment, leverage is increasingly defined by who controls the safety of the transit route. This photograph captures the historical geopolitical tension that made these lines targets in the first place. Europe's heavy reliance on Russian energy created a political entanglement that ultimately weaponized the infrastructure keeping the continent warm. To defend this territory, operators are establishing a new front line. They deploy embedded fiber Bragg gratings, optical sensors that constantly monitor the steel for strain, alongside AI-driven robotic bots designed to guard against both metal fatigue and foreign sabotage. Modern geopolitical hegemony is no longer secured by terrestrial borders. It is permanently tethered to the physical integrity of underwater steel. When the compounding pressures of hydrogen embrittlement and deep water depth finally overcome the steel, the structural failure is instantaneous. A microscopic jagged hairline fracture violently rips across the primary deep water line. This reality exposes the 2026 repair gap. At these depths, the bathypelagic environment is too toxic and overpressurized for human diver intervention. As seen in this image, specialized remotely operated vehicles, or ROVs, act as the absolute last line of defense, preventing a total supply chain collapse. As the ROV struggles against turbulent, shifting sediments and crushing pressure, the immediate economic shockwaves hit the surface. Automated shutoff valves slam closed, instantly choking off regional gas supplies. A localized physical fracture, measuring just millimeters across, instantly translates into a cascading continental energy blackout. Looking to the next decade, the rapid depletion of shallow reserves is aggressively forcing the energy industry into even deeper, strictly unrepairable oceanic depths. This forces the rise of fully autonomous subsea processing hubs, massive automated factories that operate entirely outside of traditional terrestrial borders and jurisdictions. It is the ultimate paradox of the deep-sea energy era. Humanity's relentless quest for absolute energy security has driven it to rely on the most deeply insecure environment on Earth. A single hairline fracture at 6,000 feet has the potential to paralyze entire nations. Dive deeper into the hidden secrets that shape our reality. Click the subscribe button, activate the bell, and see you in the next scientific investigation beyond the boundaries of reason, only on TEMBODocs.